right, let's get started. Good morning, everyone. Hopefully you're doing fine. So I'm launching, in my other classes, not for you guys, I'm launching a couple of the real tests today in the Top Hat / Practorio thing. So we'll see how that goes this afternoon. So had to stay up a while to get all that set up last night. So fingers crossed, let's hope it actually works out and all the issues that have been going around are contained. So as I've been sending out emails, yeah, like I told you guys, I'm not sure what's going on. I'm not sure if the problem is local. I suspect it might be local, but it might be something with Proctor themselves, but everyone's looking into it. And hopefully by this evening and tomorrow, everything will be great. So as you guys probably know, I'm having your test tomorrow during class time. So during regular class time. So not at this common meeting time, because I believe some of you have an 8:30 a.m. meeting for 1206, and we will be having the test during that meeting. So tomorrow during regular class time is when your test will be. And in general, I will have it open 15-ish minutes early. So you guys can log in, get set up, get settled, and if you can get in, if for some people it just takes them a while to log in, 10 minutes or something like that. So you'll have enough time to get in so that by the time class starts, everything should be ready and yeah, so that's just that. In terms of us now moving forward for today's class, let's share the page. And I suppose at this point we can talk about material, and maybe towards the end you guys can ask me some more about the test if you're curious, or things of that sort. So you guys already have 2 written practice tests and you have an online practice test. So you guys have like 3 practice tests going. 2 of them you have the solutions for, the third one I didn't have a chance. That being said, the test covers everything up to substitution. And in addition to that, the material that you'll need to know for the final is going to be integration by parts and the applications of integrals. So being able to find areas between curves, being able to find the average value of a function. Yeah, I think that's it. So in that regard, I guess, are there any questions, comments, concerns, issues, and yeah, go.
Can you do a couple U substitution examples?
Sure, just random examples, or do you have it? So random U substitution examples. Okay, how about this one? 3x squared over the cube root of 4 minus x minus 5x cubed. Let's go with that. Yeah, how does that one hold you? do we see what to do with that one? I just made that up. Thought I had the textbook beside me here. I can just grab some random examples from there. But yeah. Ideas here? You see that? What would you try? Right, so Alejandro has a suggestion. He wants to go with the fancy u cubed substitution. So u cubed is equal to 4 minus 5x cubed. You would differentiate both sides. So this means that 3u squared du would be minus 15x squared dx. You can solve for the dx. So that would be minus 1 over 5 u squared du is going to be equal to x squared dx. If you want to solve for the dx, you can move this guy completely over. Let's move him completely over here. So I'm going to divide by So I divided by minus 15x squared. The 3 goes into the 15 5 times. I mean, we could write it. So 3 over 15. This goes into that 5 times. So you'd have minus u squared du over 5x squared is equal to your dx. And now you just go and you plug that in. So we would have 3x squared and in the denominator, since our u cubed is this means that our u is actually the cube root. So this entire thing here gets replaced by just the variable u. Times, now my dx gets replaced by minus u squared over 5x squared du. The x squares would cancel, which is good. We want that. The u's would cancel. And I can factor out a negative 3/5. And I'd be left over with u du. So that gives you u squared over 2 plus a constant. And so that would be minus 3 over 10 of, now I can replace my u with what it was. It was 4 minus 5x cubed. It was the cube root of this, so this now is 2/3. So that's that. So see something like this, you realize that the derivative of this guy is very similar to that guy. It's just off by a constant factor. And so you realize that substituting this will make things simpler. It's in the denominator, it's under a cube root, it's several terms, it's making it complicated. So your substitution, you want to make it simpler. So you definitely want to replace that expression with like a single variable. The fact that there's also a cube root means you also have the option of simplifying while substituting. Coming in. Oh, the u squared over 2 comes from the antiderivative of this. So the antiderivative of u is u squared over 2. So that's using the power rule. Okay. So
do you have a preference in the final answer if we write like out the cube root or to the power of like 2/3?
No. So that whole thing is like, I'm laughing because I saw a meme about it last night when I was looking up memes. Okay, so there's a whole thing about, oh, you have to write your answers in a certain way or unless it's wrong. And after pre-calculus, they don't care. Like, they don't care. Like, there's this idea that, oh, you can't have a radical in a denominator. Like, no, it does not matter. We don't care whether you write it with a negative power or not. So at this point, any variation on this that is algebraically exactly the same thing. So if you wrote this as 3/10, and then you wrote this as the cube root of 4 minus 5x cubed plus c, and then you square that, that's also fine. So whether you want to write it with a radical or not, it doesn't matter as long as you have the correct answer. But yeah, it's funny how some students are like, it's almost like they have PTSD or something, and it's like, oh, you can't have a radical. No, can we write a fraction in the power? Like, yeah, of course, you can have a radical in a denominator. It's not illegal. You don't have to avoid negative powers or anything like that. Yeah, it's too funny because I'm thinking of the meme in my head. It was a Thanos meme too. It was just but it's true. So a lot of times students are worried about the exact form that they have to have the answer in, and as long as you have it exactly correct, that's what's important. So this is not what I'm gonna squabble over. So it's just make sure you can do this. And of course, I can do something copy. Let me just do the other way, because I know not everyone likes doing it the way that where they do it like a u cubed or something. So yeah, so without doing the u cubed, and so you can compare what the differences would be. So what if you're like, I'm not really comfortable with the whole u cubed or u squared substitution. If you're that kind of person, it's fine. There's nothing wrong with that. But here's how it would look in that situation. So if you just like, I just always substitute a variable u. 4 minus 5x cubed. Your du would be minus 15x squared dx. Then you would solve for the dx. So that would be du over minus 15x squared. And so now you'd plug that in. So it becomes the integral of 3x squared. We have the cube root of u here. And your dx becomes du over minus 15x squared. And now you just start simplifying, so the x squares would cancel, so that's good. You don't want any residual instances of the old variable. You want to change everything to the new variable. And at this point, I can cancel the 3 into the 15, and that's 5. And so I can factor out the constants. So it's minus 1/5 comes out, and what's left inside is du over the cube root of u, right? So you end up with an integral that looks like this, which again, not terrible. Personally, I would prefer this, but this is not terrible. If you wanted to do that one, of course, you'd write it as a power. So you'd write this as u to the minus 1/3 du, and then you just do the power rule again. So you add 1 to the power. So adding 1 is just like adding 3 over 3. So that becomes minus 1 over 3 plus 3 over 3 gives you 2 over 3. Then you divide by the new power, so you multiply by 3/2 plus c. You would get minus 3 over 10 u to the 2/3 plus c, and then you can substitute your u, minus 3 over 10, boom to the 2/3, and it was 4 minus 5x cubed. So as you'll notice, we have the same answer. It's over here. And just slight variations on it. By doing a u cube substitution, you kind of save yourself from needing fractional powers here. So you have to, instead of doing u to the minus 1/3, you just have just the u, right? And it's just So it makes it slightly easier. There are situations where it can actually save you a couple steps, but it's not terribly necessary. It's really just a personal preference. So if you just like going up your straight up U substitution, that's fine. You want to have things work a little more cleanly, just sacrifice a little bit more work up front. So this line is going to be a little bit more complicated than this line. But once you pass that point, the actual work is a little bit cleaner. You don't have to worry about fractional powers, that sort of thing. But that's how that would look. And yeah, so that is a substitution problem. Any questions on that, or? And was in terms of I guess kind of what you guys are worried about, if anything, you really shouldn't be worried about anything. You don't want to psych yourself out. But is integration the only thing? Like, how do you guys feel about all the other topics? Because this test covers, let's make sure I'm not computing or forgetting anything. So yeah, so computing integrals, which is we've been talking about, optimization is in there, motion problems is in there. So that's the thing that talks about, you know, if you have an object moving at this position, find its velocity, find its acceleration, or usually it'll be going backwards this time. The mean value theorem, absolute extrema, computing the derivatives of definite integrals, which I believe we spoke about a little bit last class. So integration is the scariest. Okay. It takes practice though. It's one of those things. Yeah, it'll be scary the first time you learn it, but if you put it into practice, it's kind of fine. But I guess you could almost say that about anything. But integration is one of those things where it really kind of clicks after a while. Like I don't think, like every other process that we've looked at, it kind of never gets easier, in the sense that, you know, like the amount of mental effort that it takes me to do an optimization problem is pretty much what it always took me, even back when I was in Calc 1. It's like, okay, I have to remember to do this step, do that step, and it's all kind of the same thing. Integration is something where if you practice enough, you can eventually do a lot of it in your head. You get used to it so well that it gets easier, comparatively speaking. But it is one of those things where, yes, the first time you see it, the first week, the first 2 weeks, the first 3 weeks, kind of, I don't know if I'm going to spot the right thing. I don't know if I'm going to see the U, and it's kind of nerve-wracking in that sense. But really, you put in the work, you'll start to see it eventually. Can we go over one of the area problems using the limit at infinity with a Riemann sum? Sure. What is a nice one to try? Okay, so let's. Yes. So let's go over a simple example, because when it comes to that, the process is more what you don't want to get lost in. So let's do something like 0 to 1 of, say, x squared plus 1. And I'll talk about, depending on the problem, how I can make it more difficult or less difficult or something like that. So let's look at this one, okay? Now you want to evaluate as a limit of a Riemann sum or something like that. So the important things that you need to remember are the following. One, you need to remember that your delta x is going to be b minus a over n. So this is for of a to b of f of x dx. So the first thing you want to know, maybe this is a bullet point, your delta x is b minus a over n. You should also realize that your I is going to be a plus I delta x. Then you're going to want to find f of xi. And then you're going to set up the actual limit. So the integral from a to b of f of x dx, this is equal to, the definition of this is limit as n approaches infinity of the sum n goes from 1 to infinity of f of xi times delta x, where these guys are done as I indicated above. Right? And then you'd have to compute that using a bunch of formulas that you'll have to memorize. Also, you need to know that the sum I goes from 1 up to n of that is n times n plus 1 over 2. You'd also have to know that the sum I goes from 1 up to n of I squared is n times n plus 1 times 2n plus 1 over 6. You'd have to know that the sum of I cubed, that goes from 1 up to n, is going to be n times n 1 over 2 squared. So you also have to know that stuff. Okay, so you have to know the process, which is this: find your delta x, find your xi, find your f of xi, plug into this formula. Then in evaluating this formula, you're going to need to know these guys. So let's actually look at that for this one. So 0 to 1 of x squared plus 1, we know that that represents the area under the curve, y equals x squared plus 1 between 0 and 1. How do you evaluate that as the limit of a Riemann sum? Well, we start out by finding our delta x. Delta x is going to be b minus a over n. So in this case, it's 1 minus 0 over n. So that's 1 over n. Then you find your xi. Your xi is going to be a plus I delta x. So that's going to be 0 plus I times 1 over n. Or in other words, just I over n. Then you're going to find your f of xi, which means you're going to just plug in the xi into your function. So now your function is x squared plus 1. So I'm just going to plug in this for x. So it's going to be that squared plus 1. And now you compute the Riemann sum. So x squared plus 1 dx. This is going to be the limit as n approaches infinity of I goes from 1 up to n of f of xi. So it's this guy. Times your delta x. So this is that, my f of xi, and this is that. Now at this point, we are just going to simplify, multiply this out. You would have I cubed over n cubed plus I over n. And your series here is measuring i's. What you can remember is anything that's not an I, you can factor out. So I can think of this as 1 over n cubed times the sum of I cubed, plus I can factor out the 1 over n, and this is the sum of I. These guys you had memorized from above. So those were these guys up here. And so now you're going to plug those guys in. So this is 1 over n cubed times n plus 1 over 2 squared plus 1 over n times n plus 1 over 2. I think something is off here. Did we miss something? Delta x is b minus a over n. So that's 1 over n. Oh, I grabbed the wrong thing. Ah. Yeah, something is off here. It's delta x that should be grabbed. It's this guy. So I grab. That's what should go here. So what's that going to do? Okay. So that's not an I cubed. And that's not going to be that, which means this is going to be here. And this is going to be here. Okay. Sorry, that should be the delta x, not, I picked and plugged in the xi. So this is going to be I squared, and that's 1. This is I squared, it's 1. This is n. And I squared is going to be n times n plus 1 times 2n plus 1 over 6. And again, that's something that you had memorized from up here. And so now you take the limit. This cancels, so that's just going to be a plus 1. And here, you're going to realize that this part here is your 2n cubed plus a bunch of stuff that we don't care about because your n is going off to infinity. So ratio of leading coefficients gives us that this first term is going to go to 2/6. So you get a third plus 1, which is 4/3. Okay. Now, one thing that the variation on this, and really this is just if the setup is just too complicated that I don't want you guys to have to go through it. Not that it's too complicated, but it'll take such a long time. If I wanted to say from like 1 up to 2 of x squared plus 1, that is actually, conceptually it's the same thing, but algebraically when you're actually working it out, that's actually significantly different from this one, because here if I jump in and I go delta x is b minus a over n. This is going to be 2 minus 1 over n. It's 1 over n. So far it doesn't seem too different, but if you go to your xi is a plus I delta x. Your a is 1. So here you get 1 plus I over n. And the fact that there are two things here makes it a little bit more complicated, because now when you go to f of xi, you would get something like 1 plus I over n all squared plus 1. And so that you'd probably have to multiply out. And so you have 1 to integrate, is going to be the limit as n approaches infinity of the sum. I goes from 1 up to n of f of xi, 1 plus I over n squared times delta x. Let's not make that mistake again. And at this point, it's just kind of annoying to multiply this out. You'll have like 3 terms to deal with. So for a problem like this, I might say something like set up a limit of a Riemann sum to compute, but I might say something like evaluate the sum using a definite integral or something like that. So if it's pretty straightforward, it's just a few things, just 2 things for you to do. You don't have to multiply out or anything like that. I'll ask you to do this directly, in which case you need to know these guys. If it's going to be annoying algebra, then I just might ask you to get to this point and then just actually evaluate the answer. And then you would know that this is actually equal to 1 to 2 of x squared plus 1. And so to compute that sum, you can actually do the integration. And so if you were to do that as a Riemann sum, the answer you would get would be this guy, would be 7 over 3. 7 over 3 plus 1. Similarly here, you can realize that if you were to do this integral using the integration techniques, you would also get 4/3. But this is evaluating an integral as a Riemann sum. It just comes down to you using this formula right here. You have to remember what these guys are and what those guys are.
So is the summation going to infinity or n? Because in like the green you wrote infinity, but then when we're doing the problem out, it's n. Or it's just infinity.
It's n, but you don't. I was mixing up notations here. It's n, but let me tell you the difference between the two. So when we write the sum, I goes from 1 to infinity of f of xi delta x. What this notation means is the limit as n approaches infinity from 1 up to n. So this whole the limit means this. So when you write infinity on the top of a sum, it really means that there's a limit that's implied. I just got a bit sloppy. So this is written as that. So a sum going to infinity means that you just take the sum going up to some number n, and then you let n go off to infinity as the limit. Yeah, so all these are sum goes to n. Yeah, I got those right. Okay. Okay, that's limited for Riemann sum. And just to see if what we did last time kind of sunk in, what if I were to ask you, what is the derivative of the integral from let's say sine of x up to x cubed of 1 over the 5th root of 2 plus t to the 5th dt. Just gonna try to make it look confusing here. How do you do that?
You could break up the limits into like different parts and then like solve each one individually, or you can do it by that formula you gave us where it's like,
Okay, so what'll just tell me. Go the whatever way you see it, move forward. Pretend this is a test and you're going. What would you write?
okay, so usually I've been doing the formula where it's like f of h of x, if h of x is on the top. So you like f of the top integral times its derivative, and then minus f of the bottom limit times the derivative of that limit.
Okay, what would it look like here?
It would be 1 over the 5th root of 2 plus x cubed to the 5th, or x to the 15 if you want to just simplify it, times 3x squared. And then minus 1 over the 5th root of 2 plus sine x to the 5th. And then times cosine x.
Yeah, that's it. Yeah. And if I gave you some function f of x on some interval a b, and asked you to find the absolute extrema, right? What would you do? Just tell me the general steps. So this is, I'm going to give you some function, and I'm going to give you the interval, and I'm saying find the absolute extrema. What's the process here?
So you first find the critical points.
Okay. How do you find critical points?
You find the derivative of f of x, and then set that equal to 0.
Something's missing.
Or undefined.
Or undefined, right? So if wherever your derivative is undefined is also going to be something that you want to pay attention to. So if when you differentiate, it puts an x in a denominator and then you have to worry about division by 0, you should worry about the x's that create the division by 0. So find the critical points. And of course, you want to find the critical points in the interval. Right? So if you have a critical point outside of AB, we don't care. Okay? Yeah, then?
And then you test those points and the endpoints of the interval in f of x.
Right, so you're going to evaluate the endpoints. Yes. You're going to test these points. Meaning, plug them into the function. And then 2, you're going to evaluate the endpoints. And that means find f when you plug in A and find f when you plug in B. Okay, so you find the critical points, you plug it into the function, you find the y values. Then you find the y values at the endpoints. Then
Then you compare, and the smallest is going to be your absolute min, and the largest is going to be the absolute max.
Right, so your smallest y value that's going to be your absolute min. And your largest and for these you would state as you want like to say f of x1 equals y1 form. Right, so you state the whole coordinate. Say f at this value gives that output, and that's the absolute max. I mean, silly example, just to make sure you have the process down. So f of x equals x squared on, say, -1, 4, or whatever. Then you would, step 1, find the critical points. So you find f prime of x. This is equal to 2x. You're going to set 2x equals 0 for 2x undefined. This is never undefined. So you only worry about where 2x equals 0. This means that x equals 0. X equals 0. This is in the interval. Right? And that's kind of a parenthetical statement. So now you're going to test. You're going to find f of 0, which you would get 0. And then you hold that off for a second. Then you're going to test the endpoints. So you're going to find f of -1, which is 1. You're also going to find f of 4, which is 16. And then you make your conclusion. So the largest value was f of 4. So you're going to write f of 4 equals 16. Well, that's your absolute max. And then you're going to write f of 0 equals 0. That's your absolute min. And that will be your answer. Okay. And all these problems are like that. The difference is like how much calculation you'd have to go through at these stages based on what the function looks like. But yeah, that's the process. Linear approximation. So for linear approximation, we're pretty much using this formula here. Your f of x is approximately equal to f of a plus f prime of a times x minus a. And this is when x is close to a. Okay, so we can use that for linear approximation. I don't know. So example, approximate, say the square root of 4.01. So here you would pick your f of x equals the square root of x because I want to measure the square root of something. Your x is, of course, 4.01. Your a is going to be a value close to x that you actually know the values for. So I'll pick a equals 4. Now we're going to find f prime of x, which is 1 over 2 rad x. And so this means that our f of a is equal to f of 4 is the square root of 4, which is 2. Your f prime of a is equal to f prime of 4, which is 1 over 2 times the square root of 4, which is a quarter. And then this would mean that the square root of 4.01 is approximately equal to f of 4 plus f prime of 4 times x minus a. So that's 2 plus a quarter times 0.01. It's 2 plus 1 over 400. And so that is 801 over 400. So that would be our approximation.
Can we do an approximation where it's the cube root?
Okay, so approximate the cube root of, say, 7.99. Then here, our f of x would be the cube root of x. Our x would be 7.99. Our a would be 8, something very close to that I actually know the values for. And so in that case, I would do my f prime of x. And that is going to be x to the minus 2/3 after bringing down 1/3, or that's going to be 1 over 3 times the cube root of x squared. So now I would want to find my f of a. And then I would find my f prime of a. So cube root of 8 is 2, 2 squared is 4, 4 times 3 is 12, so that's 1/12. And so now I can plug it in. So the cube root of 7.99 is approximately equal to our f of 8 plus f prime of 8 times x minus a. So that's going to be 2 plus 1/12 times minus 0.01. That's 2 minus 1 over 1200. And so this is 2400 over 1200. So it's 23.99 for 1200. That's not. So yeah, once you really get used to things, you'll realize that the processes are very similar. The difference is the actual functions. The details change with the function you're doing, but overall, you'll notice that I kind of do things in the same way. So what is f? X, a, find f prime, find f of a, find f prime of a, plug into the formula. Here, what is f of x? X, a, f prime, find f of a, find f prime of a, plug into the formula. You kind of just do the problems and over and over and over again. And so to the point where even when I'm just like randomly writing out solutions, my solutions are actually very similar to each other because the process in my head is the thing that I'm going over. And the details just depend on the function. When it comes to the details, that's just me applying some derivative rule. But I kind of think of things in the same order all the time. And once you kind of do things that way, it's actually not so bad. One of those things that kind of gets students in trouble, that makes them feel like things are more confusing than they are. And you guys can, if you happen to be someone who's really confused, you can go through your notes and look at how you practice problems. And if you're doing two of the same problem types and the structure is different, then chances are you're going to be confused. You're going to be like, oh, this topic is so confusing and da, da, da. You're not really going to have a handle on it. But if you do a certain type of problem, you do it in the same way all the time. You always do this thing first, then you do that thing second, then you do that thing third. It becomes ingrained in you. Then you'll start to see the patterns with everything. And then you'd realize that, oh yeah, once I have the process, then it doesn't matter. Jhevon can throw whatever example he wants to in this cookie cutter problem, and I'll be able to deal with it. So yeah, pretty much go through the problems in the same way. So a part of it, which as I mentioned, is like I would ask you guys here, what would be the steps that you would do to solve a problem, right? So right here, I didn't even give you a specific example. I just said, suppose I gave you any random function on an interval. How do you go about the process? Same thing. I could have asked you, what would be the process of linear approximation? I wrote down the formula here, but given a linear approximation, what is the process? Well, step 1, find f of x. Step 2, identify your x. Step 3, identify your a, because it's going to be the number that's close to x that you can know the value for. Step 3, you're going to differentiate. Step 4, you're going to plug in a into your function and the derivative. Step 5, plug into this formula. So you really want to go into things with that sort of mindset. And it's a little bit algorithmic. I'll admit it's a little bit kind of like trying to turn yourself into a computer program. But at this level, that's kind of how you want to learn math. You just want to learn it very like algorithmically. Later on, creativity actually comes in play, but you actually need to know how to paint by the numbers before you go off and be Picasso. You know what I mean? So you really want to have the methods and the strategies in your mind, have all the formulas, know when to use the formulas, in what order, and always do every single problem in exactly the same way every single time. Always do the same thing first, the same thing second, the same thing third. You want it to just be something ingrained in you that's almost automatic. Yeah. Anyway, we're pretty much out of time. As I mentioned in an email, I opened up the mock test, the online version again. It closes tonight at 9 p.m. Just want to make sure that whatever issues you guys are having, log in, try to figure it out. If you're having problems with hardware, your webcam isn't working or anything like that, figure that out by tomorrow's class, because that's when the test is going to be, and it's going to be very similar to the mocks that I've posted so far. You can see at this point I gave you like 3. They're all kind of the same thing. If things look different, they're different in this particular way. It's just like me replacing an example in some spot. So instead of doing something with a square root, you know, I might ask you to do the same thing with a cube root, right? So that little variation on detail you should be able to deal with, but overall, you know, the mock test material, you know the topics, you know how to deal with all of them, then you will be fine for the test. And so pretty much all you have to worry about now is just to make sure, okay, all right, I'll see you, Dylan. Yeah, got to get out of here. We're getting out of here. So take care, good luck, and I will see you guys around. So, all right, take care, Steve. We'll stop there. As always, I will post the PDF of this under the video when I post the video. And so when this finishes, when the video finishes processing, I will share that with you guys. That being said, stay safe and keep studying. I'll see you guys around. Take care.